In the beginning, there was GL begin and GL end, and it worked, and you're using it, and we like it. It's easy to learn, easy to understand. However, it is very inefficient. And you can imagine having the CPU generate a GL vertex 3F function call for every single vertex you want to draw. Yeah, okay. There must be a better way. And in OpenGLES, there is no other way. So yes, we want to talk about vertex buffer objects. Here's the general idea. Imagine we've got this cube, it's got 8 vertices. Why not make a table out of it? Put the table in GPU memory on the graphics card and then point to the table and say, here, draw this. Well, okay, one, it's tremendously more efficient because it's on the graphics card. You don't have the CPU generating these calls. And two, there's no function. Well, there's one function call that says draw this, but other than that, it's only one call. So this is what vertex buffer objects are about. And remember, anytime you see the word object in the OpenGL world, it means on the graphics card in GPU memory. So that's why it's called not just vertex buffer, but vertex buffer object. We can do it with triangles. Again, there's nothing magic about that. It has to be quadrilaterals, but yeah, we can do it with triangles as well. Okay, now, surprisingly, this does have something to do with computer graphics. Did you ever see the Star Trek series, Star Trek Deep Space Nine? It didn't take place by a ship traveling through space. It was a space station. And they did a lot of unloading cargo, picking up supplies as good space stations should do, and there were docking ports. Okay, and so when a ship wanted to come by, it would dock at port A, and they didn't have to say, go service the name of the ship. They said, go to port A. Whoever's at port A, load these supplies, take these products in. Yeah, it was easy. So OpenGL has the same thing, except instead of a space station, it has its context, which we often call the state. And this is what keeps GL Vertex 3F from having 50 arguments, is what OpenGL does is it docks, I call it docking, they call it binding, it docks the information to places on the state. Okay, and so yeah, there's a current color going on, there's current lighting information going on, current transformation stuff going on, current textures, but there's also a docking port called array buffer and a docking port called element array buffer. And to the docking port called array buffer, we basically place a pointer to that table. And to this other docking port called element array buffer, we place a pointer to the indices, how to connect things up. Okay, so this docking port has vertices and potentially colors, surface normal vectors, texture coordinates. This docking port has indices, a pointer to the table of indices. So it's great. And now all you have to do is say draw. That's not the name of the function. We'll get to that. But all you have to do is say draw, and it just goes out to whatever's plugged into those docking ports and uses that information. And so this is way more efficient than GL begin, vertex, 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 GL end. And that's why we're covering it. Okay, um, remember they call it bind buffer. Again, I call it docking because I like the Star Trek metaphor, but that's how you plug that's how a pointer ends up pointing out of the array buffer port. And then there are other functions that make these things work. Like for instance, there's a GL buffer data where you have a pointer to your array of data, how many bytes you've got, and how you're planning on using it. We'll come to that in a moment. Okay, um, so when we're ready to draw, so you bind the buffer, you load your vertex data, and then when you're ready to draw, the name of the function is actually GL-draw-arrays. You tell it what the topology is, you tell it where to start, and you tell it how many vertices. Notice there's no pointer to the data. Well, that's because the data is sitting at the docking port. So really what this is saying, what draw array says is whatever's sitting at the docking port, go draw it. Use this topology, good to know the topology, start here and do that many vertices. And the reason they have a starting index is if you want to be even more efficient, you put several objects worth of vertices in that one buffer object. And now you say, oh, draw the first 1,000. Oh, now draw the next 2,000. And so you don't even have to load multiple vertex buffers. It just stays on the same docking port. Okay, so if you were doing the state thing in C++, if you were rewriting OpenGL, well, what would you do? Well, you would have places to put tables of information. Well, that's essentially what this is doing here, is that gen buffers is giving you an array, a place to put all this information. Okay, here's how you go about doing this. Buffer data, what type it is, which in the case of the vertices is array buffer, number of bytes, pointer to the data in your arrays, and then this thing called usage. Usage is an interesting argument. Basically, it's a hint. It is of the form GL, a constant, a constant. And the first constant can either be static or dynamic, and the second one could either be draw or read. So static draw is the one you would use most often. But basically, this is a hint to the OpenGL driver about what memory to use to hold this buffer. And so if you're going to be reading, it may put it in some special place. If you're going to be doing dynamic that is constantly rewriting it, it may put it in another special place, or it may ignore the usage argument completely. It's there as a hint. Static draw is typically what we would all want to use. Okay, so step one, fill your own arrays with the drawing data. It could be all vertices, it could be vertices and colors, vertices and normals, vertices and texture coordinates, or all of them together. You create the buffer handle, you bind it, and you load it. This is how many vertices I'm going to put in there. I'm just going to say it's only vertices. Well, each vertex is 3 floats here, and times the number of vertices. Here's my array and static draw. Now that transfers all of that information over to GPU memory. All right, to draw it, you're going to talk about what things you want to draw. You know, you're going to make either 1, 2, 3, or 4 calls to enable client state. And in each one of those calls, you're going to put, well, you better have a vertex array, otherwise there's nothing to draw. But you can also have color, normals, textures. Okay, you are going to basically set up all of those, or what you're saying is, here's which ones I've set up. Now, here's the trick. The trick is we need to tell it where to find those things. And there's 2 ways of storing things. One is if I say I have vertices and colors, okay, colors for at each vertex, I could put all the vertex data here and then put all the color data there, meaning this vertex has this color. This vertex has this color. Okay, got to correspond. Or I could interleave them. I could put one vertex here, XYZ, one color, RGB, XYZ, RGB, and so on. And it doesn't matter, it'll work just fine, but you have to tell it. And so when you're setting these up, you tell it the size, the type, the stride, and the offset. Okay, size is how many numbers per vertex do you have? For XYZs and RGBs, it would be 3. For RGBA, it would be 4. For normal vectors, it would be 3. For S and Ts, it would be 2. Okay, the type, what do you have? Are they floats? Are they ints? Typically in our world, they would be floats. The stride is, all right, time out a moment. Yep, sounds like the Amazon delivery truck. Yep, that's worth barking at. Okay, so the stride is the byte offset between consecutive entries. If I'm going from vertex data to vertex data here, well, I would make the stride 0 because 0 means as tightly packed as you can possibly get. Or you could just say the number of bytes you have to advance in order to get to the next vertex. It has more meaning here because the stride would be from here to there. How many bytes would that be? Okay, and the offset is where do you start, which for this arrangement would be 0. For this arrangement would be 0, starting the vertices. This would be however many bytes it takes to get past the vertex data. And the start of the color data would be the size of 3 floats. Okay, so if they're packed, again, we've got 3 numbers, X, Y, Z. They're all floats. Here is the stride. Like, how do you get to the next one? Well, the next vertex is 3 floats past the current one, and you start at the top. And if they're packed like this, here's how you do the colors. There's 3 numbers, RGB. They're all floats. Here is the stride. You need 3 floats to get from one color to the next color. Here is where you start. You start way down here. Okay, now if you've interleaved it, same sort of thing. I've got 3 numbers, X, Y, Z. They're all floats. In order to get to the next float, I have to advance past 6 floats, X, Y, Z, RGB. Now comes the next X, Y, Z. Color pointer. The stride is going to be 6, just like here. And the starting place is going to be 3 floats into the array. Okay, and this is exactly what you would do if you were setting up C arrays or C arrays of structures. Okay, ready, set, draw. Draw arrays. You don't have to tell it where the data is. It's already at that docking port. Okay? What if your vertices need to be accessed in random order? And I don't mean random like flip a coin, pick a vertex. I mean, what if they're not all in order? Like the example we had a moment ago is we're assuming that XYZ, 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 okay, there's our triangle. Well, what we do is we create a table of indices, and that goes on the second buffer docking port. Okay, so if this is what we've got, it goes on the second buffer docking port. We set up this exactly the same as we did before, exactly the same as we did before, and we call GL begin, we call GL array element, and we say we're going to connect up in a quadrilateral vertices 0, 2, 3, and 1. And so, yes, here's our quadrilateral 0, 2, 3, and 1. So the vertex data and the color data are already on the first docking port. Now we're going to put a table of indices on the second docking port. And this all works, but we still have a problem. Gosh, we are doing a whole bunch of calls here. We're doing GL begin, we're doing GL end, and we know already that those are pretty inefficient. So there must be a better way, and there is. Okay, we put the indices over in a table. Okay, the array buffer is vertices, colors, normals, S and T. The element array buffer is the index or the integer table, and we call draw elements. And again, we don't have to point to any data. There, the data is living on docking port, the first docking port and the second docking port. So draw elements is what you do if you've got the index table. Okay. Now, what if you want to fill the buffer without having to create an array of information on your own on the CPU? There's this wonderful call called map buffer. And what it does is it returns to you an address, and that address actually points into GPU memory, but it looks to your program like it's a CPU address. And so at that point, it looks like you have an array called that, and you just start filling it exactly like you would do in C++. Okay, so here we say map buffer, and now, well, if this was an array of structs, we would just fill it exactly like this. And so, if you do this, be sure to unmap it. Otherwise, it really is going to kind of mess up with the memory management. But this is a really handy thing to do. I like it because it makes your code look like you're just filling a C array, when in fact it's actually flying across the bus into GPU memory. Okay, it's a little bit painful to build up those tables. And so we built a vertex buffer object class called vertex buffer object. Clever, huh? And okay, so we're going to create one in our program called VB. So we would typically put this in the global variables. And now the methods are what you would do if you were using begin end. So vb.glBegin quads. We're not doing begin end, we're doing vertex buffer objects. But it looks like we're using what we already know, begin end. And there's a color 3f method, a vertex 3f method, and there's a draw method. So you don't have to worry about the size, the strides, the offsets. Just fill it up like you already know how to do. And then when you say draw, it actually, the first time you say draw, it sends the vertex buffer object over to the GPU. And then every other time you say draw, it just draws what's already there. These are the class methods. You have this code. It's in the downloadable files part of the resources page. Have at it if you'd like. Yep, there it is. Yep, text coord 2f. You can also print it out if you would like a record of what you did, or if something's not right, you can print out the vertex buffer object and see maybe where it's going wrong. You can collapse vertices. And remember back on the cube, each vertex was actually shared by 3 quadrilaterals. So if you want to, you can list each vertex 3 times when that quadrilateral is defined, or you can have it, when it uses the same vertex again, you can have it say, wait a minute, I've already got that. Here's its integer index. Go do that. If you want to do it that way, that's called collapsing the vertices. And here we go. Collapse the common vertices and tell it true or false, depending on if you want to do it. The caveat right here is, after a while, it becomes kind of slow because it's trying to look at the entire table of vertices and see if you've already got one that matches that XYZ. So yeah, be a little careful about doing that. It makes your buffer smaller, but it makes your vertex buffer smaller, but it may kill you in time. Like here it is with you, if you do collapse the vertices, that is, here's a quad, it uses vertex 3. This one uses vertex 3. This one uses vertex 3. If we don't collapse the vertices, well, now our table is 3 times longer because each vertex shares 3, or each corner point, it really has 3 separate but identical vertices. And now we have 3 and 8 and 21. So yeah, makes our vertex table bigger. Again, you can control this. And using vertex buffer objects with shaders works great. If we look at this, this looks very much like we've already seen, right? Is we have colors and we have vertices. Here's how you do it. You ask for a certain variable name. The API for the shaders returns you a location in the symbol table, and then you simply use that to fill with the data you want. Okay, and so when you say draw arrays, it's going to send the contents of that vertex buffer into your vertex shader under the name a vertex. And so this works great with shaders as well. So you can use it within the fixed function, or you can use it in the shaders. You're not required to use vertex buffer objects in any of our projects. You really, in the projects, we're just asking you to make it work and make it work well.